Hi, this is Eric with Math from the Gut, welcoming you back to our last test drive of the Pythagorean Theorem. In this video, we're going to test drive an upper limit for h. In other words, can we find some length that is so long that the actual value of h is guaranteed to be shorter, or perhaps equal to that length? Once again, we'll start with the general triangle having lengths of x, y, and h. Is there some value, some mathematical combination of x and y that h must be shorter than? You might want to pause and ponder on this a bit before continuing. If you can't think of anything, follow along as I start discussing a possible upper limit, and see how quickly you can discover where I'm going, and perhaps figure out this upper limit for yourself. So, with some help from Google Maps, we'll start off with a map of a big chunk of the United States. Let's say that we want to travel from San Diego, California to Minneapolis, Minnesota, using the shortest path possible. Assuming here that the Earth is flat to keep things easier, I hope you see that our shortest distance is a straight line that goes as the crow flies. Any other path takes us off of that line and causes us to travel more miles. For example, if we started out going east instead like this, we would end up very far out of our way down in Louisiana. Then we would have to make up for that by going a long distance north to reach Minneapolis. Can you figure out the upper limit that I'm working towards yet? Okay, as you probably noticed, I managed to sneak in a right triangle here. So let's give it its due and put in the proper labels. Does this help? Alright, let's look at this a different way now. First, we'll remove the map, move the triangle up a bit, and then spin it so that its hypotenuse is now going straight across. Note that we haven't really changed anything. It's still the same triangle that was on the map. Perhaps this makes things easier to see? If we want to go from the green dot to the red dot, hopefully, it's clear that the shortest path just involves going straight across along h. Notice that when we go along x, that we're wasting a lot of effort going down. Then when we go back along y, we waste a lot of effort going back up. So, do you now see some quantity that h must be shorter than? Come on now, this is your last chance. Think a bit if you need to. Hopefully you saw or can see now that h must be less than x plus y. This means that x plus y is an upper limit for h. Now, we'll test this upper limit with some numbers. And keep in mind that seeing things work with specific numbers, it may give us a good feeling, and that's important, but it can never be used to officially prove things in general. So let's invite our old friend back, the 5, 12, 13 triangle. Since we already did this, we're not going to compute h again. So in this case, h equals 13. And x plus y equals 5 plus 12, or 17. Since 13 is less than 17, this tells us that h is less than x plus y for this one case. Now, let's see if this upper limit holds in general. What we need to do here is compare h with x plus y. Mathematically, the difficulty is that the Pythagorean theorem for h has this pesky square root sign in it. So how do we compare the square root of the quantity x squared plus y squared with x plus y? The trick is to get rid of the square root sign by comparing h squared with the quantity x plus y squared. Remember from before that whichever number is higher will also have the higher square value, so we can compare the square values instead. So let's do the math. It does get a bit involved here. I try to break it down into small steps, but you may not be able to follow all of this, especially if you haven't taken algebra before. But please, don't hate me and beat yourself up if you can't follow everything here. Really, skip this if it becomes impossible. So, h squared equals x squared plus y squared as we've seen before. It's just the Pythagorean theorem. We are going to compare this with the quantity x plus y squared. Again, keep in mind that we're comparing h with the quantity x plus y by comparing h squared with the quantity x plus y squared. First, we note that the quantity x plus y squared can be expressed as the quantity x plus y times the quantity x plus y. We now expand this by using the distributive property. Notice how I colored the first x and y red so that we can keep track of where those particular x's and y's go. The first thing we'll do is to multiply our red x by the number represented by the black x plus y. This gives us x times the quantity x plus y. Likewise, we multiply the red y by the same black x plus y to get y times the quantity x plus y. We now distribute the red x over x plus y to get x times x plus x times y. In the same way, we then distribute the red y over x plus y to get y times x plus y times y. Next, we rewrite x times x as x squared. Since x times y equals y times x, this becomes 2 times x times y. And finally, y times y is y squared. Rearranging a bit gives us this. After doing all this, how does h squared compare to the quantity x plus y squared now? You might want to pause and ponder on this for a moment. Okay, the first thing I notice is that they both have the same x squared plus y squared term. The only difference is that the quantity x plus y squared has this extra 2xy term. Can you think about what that term means here? Keep in mind that for normal, non-degenerate triangles, x and y are always positive. So what does that tell us about this extra term? You might want to think a bit here. Okay, because x and y are positive for triangles that haven't collapsed, 2xy is also positive since 2 multiplied by the two positive numbers x and y will always be positive. This extra positive term that we see in the expansion of the quantity x plus y squared tells us that the quantity x plus y squared will always be greater than h squared for non-collapsed triangles. Let's write this on a new page. Next, we take the square root of each side. This finally tells us that x plus y will always be greater than h for regular triangles. Woo! That was quite a lot. Please, play this over or think about it if I lost you somewhere. The same equations also work for degenerate triangles that have collapsed into a line or a point. The only difference is that the extra 2xy term now equals 0 since x and or y is 0 for degenerate cases and anything times 0 is 0. So what does this mean when we compare h with x plus y? You might want to pause here. Well, we see here that h squared and the quantity x plus y squared now both exactly equal x squared plus y squared since 2xy is 0. This means that h equals x plus y for degenerate triangles. This should make sense since the term degenerate triangle is just a fancy way of saying a point or a line. Our triangle is collapsed where h is either equal to x or to y or to 0. So there's no possibility of wandering off the hypotenuse and going extra distance when we move along the legs. So, in general, we have shown that x plus y is an upper limit for h for both regular and degenerate triangles. With some effort, you can see this property pretty quickly whenever you look at the Pythagorean theorem by noticing that additional positive 2xy term when we square x plus y. But for me, at least, this is the most difficult test drive to see very quickly by inspection, at least without using some ideas in more advanced math called calculus. We are now finally done our last test drive. In the final section, I want to discuss the many reasons why I always test drive every equation that I see. As always, please leave comments and become part of the Math from the Gut Dream Team. See you in Part 9.